So out of distribution generalization via task extrapolation. The IRM paper or invariant risk minimization paper, right, describe the challenge that this faces very eloquently. You have a data set that contains images of cows and camels, and your task is to predict whether a given image contains a cow or a camel, right? Very straightforward problem that you would use a CNN, ML, like fully connected layers and then solve it. Fantastic. It's very easy for a CNN to handle this kind of task and will probably score very well on it. But the data set will contain information about the environment that will inevitably make its way into the image itself, right? And that environment could be such like that of a grassland for a cow, and for a desert it would be that for a camel it would be that of a desert, right? That is what you would expect. And because of that, what happens is that the model learns a spurious correlation. It doesn't really learn the actual information that is relevant for a cow and a camel. It will learn that when there is yellow color in the image, predict camel, and when there is green in the image, predict cow. And it will do very well 90% of the time. But that is not our objective. Our objective is to identify the actual or generalize to the actual definition of the object, right? And that's where the phrase comes, like learning to define a cow, because the cow is not defined by the environment it's in, is defined by the object itself. And without sort of diving into the philosophical definition of a cow, that's what we really want to fundamentally generalize to. So today we will talk about the task description, which I gave you guys a forward to, and then we look at more of the statistical observation or a statistical way of looking at the same challenge. We will talk about risk-aware optimization, which is basically understanding the fact that there is a spurious correlation and optimizing such that we ensure that it tries to at least generalize to the object itself and not the environment or any spurious correlation, whether that be an environment or any other object that is present in that correlates with the labels. Next is risk extrapolation, which is what this paper actually discusses, where instead of I will discuss the challenges with risk-aware optimization, and it sort of fixes that kind of, and then we will discuss evaluation and how that performs. So let's start with the task distribution. We can assume, or we can look at training a neural network like a task where you have to model a multivariate distribution, right? Your X is your input data, right? Any features that are present, such as the image itself, and Y is the prediction label. That's the target that we want to look at. And the distribution for something that is univariate. So, for instance, just always not univariate. Let's say just we have X and Y data, and we need to predict it. That would be, or let's just say we have not multivariate but two-dimensional data, and the X's are like one type of data, the O's are the other type of data. We just generate a predictor, right? So we are modeling the statistical distribution, and this is a two-dimensional statistical distribution. And by generating a representation of this distribution, we are able to predict whether or not a model is, whether or not the label is square or circle, basically. And that's sort of the statistical implication of it. And the general objective when we look at it like a statistical distribution is to maximize the likelihood of the data. So if we are taking a linear regressor, we will have a line that we are trying to predict, right? So there is one weight and one bias. And we basically say that given the weight and the bias, we want, given the weight, the bias, as well as our training data, we want to maximize the likelihood of actually obtaining this distribution. So the reverse of probability, basically, right? So in probability, you are given data, you're given the data and you have to predict the label, you are given the data, the weights, and you have to predict the label. in the likelihood you are given your weights and wait, did I say it wrong? You're given likelihood is
And the label because
You get given to the weights and the labels, I think.
yeah, because it's X and Y.
Yeah.
right. And we have to basically predict what set of weights will give the maximum likelihood of having such a distribution. So that's just generally the likelihood function. And this is almost too powerful, and that is because most of the models that we use today are over parameterized. That's because the data set that we have, even with the terabytes and terabytes of information that we potentially sort of work with, what ends up happening is that the data is very similar, right? It models a very sort of specific distribution in that all of the variables have or all of the variables belong to a certain domain or certain environment, right? And when they belong to that single type of domain or environment, it is very easy for the likelihood function to actually predict on the basis of that single distribution itself. Because what it's doing is it is predicting the likelihood, maximum likelihood of the distribution, not the actual information that we want to encode, or not the actual definition that we want to encode, right? It is encoding the distribution, not the definition. And that's where that sort of disconnect comes in. So maximum likelihood does not care about the causal basis for the data. It doesn't care about why this distribution looks like this. As long as it gives it the highest probability, it says that these are the best possible weights. And that is basically where it will leave it. So what this results in is our model fitting to a spurious correlation in the data set. I have this missed it. Okay. We can specify the potential spurious correlations that we can expect to occur as groups for the sake of argument. During our actual practice, we do not expect there to be this group information, but for the sort of lab grown examples where we want to evaluate how well a given model or a given approach works, we split tests or we split our test sets by group and then evaluate how well it works individually. So this is an example of that. I made up the information completely, but the idea is kind of this is kind of we have the idea is kind of represented, right? So we have this data set, okay, and this data set contains 4 different groups or different environments, and we get the accuracy and the loss of each of these groups, and we can see that there is a trend in that the accuracy keeps reducing as the groups as we go from group 1 through 4, and the loss keeps increasing as we go from 1 through 4. So it's performing worse on group 4, 3, 2, but it's performing very well on group 1. And the reason for that is the fact that we have disproportion information. When we calculate the loss, right, for a given set of weights, the loss is basically the average error that we get, right? Mean squared error, mean average. So when we get the average error, what ends up happening is that since we have all of this data that belongs to group 1, it overpowers our model, and the loss is very high if the group 1, if this group 1 is not fitted correctly. So what happens is that we have a model that is very complicated, and we want it to generalize to a certain bit of information, and we say, oh, I have 10 terabytes of data. There is no way that it overfits to this set of information. But what ends up happening is that it will overfit to group 1 and underfit to group 4 simply because that drives that average loss. And since we don't normally know what this group information is, it becomes very hard for us to tell if it is actually generalizing properly or just overfitting. So while the overall accuracy of this training set is maximized, it assumes that in practice you will also see that group 1 is 90% of the test set, right? And this we do not have an issue with this because going back to the cow and camel example, right? You will not expect to see a camel in a grassland, and you would definitely not expect to see a cow in a desert, right? It's just not likely to occur in real life, which is why it's not so much of a problem. but our fundamental objective is to ensure that we can recognize it everywhere. And a normal human will not make a mistake because it looks at the background, right? Maybe it does for some certain set of information if they don't know about what the class is, but for something like a cow and a camel, it will perform better, or it will not make the same set of mistakes. So normal neural networks have superhuman performance and have shown to have superhuman performance on a wide range of tasks, but they don't show superhuman level intuition, and that is what we want in our model. So the prediction on an input from group 4 is too inaccurate to be even considered. It's as good as just random chance, right? So to correct this, our new objective is to ensure domain robustness. Our model should be must generalize to a new unseen test domain, and that test domain should work perfectly. So we should be able to get information from a new environment that it has never seen before, and it should work completely okay. And that is when we know that we've actually learned about the object itself and not a spurious correlation. So we can formalize this as a perturbation set of risk, right? And risk is what we really are looking to define here. So the risk is basically the expected error if you are attempting if you are attempting to predict the information that is outside your training set, or outside your training set. Let's assume that for the case of this example, we have for this example our training set is working perfectly, right? So we want to, so F is the set of possible test domains, environments, and theta is our predictor, which is our neural network, right? And our objective is to maximize the number of environments that can be predicted with our predictor, predicted accurately and reasonably with our predictor. And the perturbation set basically means that it is an approximation of all of the domains that we have, because it is impossible, like some mathematical reason that I do not know. It is not possible to obtain or it is not, computationally possible to calculate or evaluate the risk for all of the every possible domain. And yeah, it's not computationally tractable. I do not know why. Yes?
Is the domain always in the training set, or is it just like something completely don't know?
Yeah, so in this case, it is completely don't know. We will all of the domain extrapolation tasks. Oh, actually, this is exactly so. This bit is exactly your question. So F cannot be arbitrary, or the set of environments, they say that it cannot be arbitrary. It has to be a set of environments that we know about, and we are restricted in our assumptions of the possible test domains. So we can only say we have, say, 5 different test domains, and we assume that this is going to be the entire extent of what we are going to cover. It's not going to be more than that, because it will not perform well more than that. So risk extrapolation, it will only cover up to the extent of we can work with information that covers maybe distributions that are in between those domains, so we can interpolate, but we cannot really properly extrapolate with stuff like IRM. And risk extrapolation is an algorithm that allows us to extrapolate a little bit, but the more we extrapolate, the less relevant our predictions become. So if we were to say, well, I think we'll cover this in ARM, but by setting this as our objective or our updated objective function, it uncovers invariant relationships between the inputs and the outputs. And invariant relationships are basically the core of what we are trying to uncover, because if we know an invariant relationship between 2 different environments, right? So like grass versus desert, then that invariant relationship will mean we actually understand what a cow is, because in our internal representation of the cow would be the same even if the cow is present in a desert or a grassland. So yes.
But is it part of like human understanding, like based on like those like external variables, just like the environment of the, like I would, like me as a human, like I would not expect to find a cow
well, ideally, we want to be superhuman, right? Humans would consider those factors, but I would not say that it's a strength, that is kind of a weakness, right? Because we assume that these set of factors will also hold, and if it does not hold, then it is unlikely, which is obviously bad, because the same object is the same object regardless of the environment that it's in. So that is also why I don't know. Yeah, I think you would, yes.
Just have a quick rundown about the first 5 slides through. I'm just guessing that it was training for a task. The domain, say like Arctic foxes in the snow, right?
Mm-hmm.
And you see an Arctic fox in the desert, and you're like, what the hell is that, right? Because the domain is obviously located.
Exactly.
So
Yeah.
that's the main goal what we're trying to fix today, right?
Yeah.
Okay.
So the idea is that, as using your Arctic fox example, right? We let's say we have a binary classification task and we have to compare camel and Arctic fox. If you put a camel in the Arctic and the fox in and the Arctic fox in the desert, the model that you would get, like the model that you would train normally, would not be able to predict the information correctly, simply because it was looking at, it will focus on the environment and not the object itself. And our goal is to ensure that we gain an understanding of the object and not the environment.
Yeah.
And if we look at, say, 4 different environments or groups, right? We basically specify that, the general loss functions that we use, like mean, squared, error, they take an average of all of the examples that we have and try to minimize those averages,
So
right?
regression, right?
Sorry.
It's like a regression problem, then, pretty much. Is that the right way to think about it?
Well, no, if you're looking at classification, you can look at it
It's a
like,
classification model, I guess as far as like the solution of it, regress to like the average solution.
yeah, that's what it does.
Yeah.
Exactly. It regresses to the average solution. And if this group information is generally hidden, we do not know this, right? Unless it is manually set up, your data set does not have information on the background. And even if it does, you generally don't know what the correlations are, right? It's something that you miss, which is why you get errors that you don't expect, or like results that you don't expect. So if we have these 4 groups as an example, and we want to predict these 4 different classes, and each of those 4 classes have a correlation to these 4 groups, right? We basically see that our group 1 has a very high accuracy, and group 4 has very low accuracy, and it keeps reducing basically. And the loss is an inverse where it keeps increasing, which is bad. And what it ends up, the reason for that is because of the proportion that we see over here, right? Group 1 is 90% of the data set. So what ends up happening is that the model prioritizes understanding that group specifically and overfits to information within that group, because though the error on getting that generalized part wrong is very high, versus getting this wrong is very low, then it will completely ignore it. So even if we have this entire class over here with this group, it is as good as a random guess when we actually run the prediction, simply because it is not considered at all. Yeah.
Is it fair to say that it treats the other groups as noise pretty much?
It treats other groups as noise, exactly. Yeah, and it ignores it, which is not ideal. And we want, even if it is possible, like even if this is like say 50 terabytes, right? Even 0.0025, even what is this? 25%, whatever. 2.5% of the data. My brain is not functioning. 0.25% of the data. Even 0.25% of the data of 50 terabytes is more than enough to generalize an understanding of this particular group. But it will fail to do that because of the fact that we have defined this group dominance.
In the next slide,
Uh-huh.
You said it uncovers invariant relationship between the input and outputs.
Yeah.
But is that an invariant relationship like with reference to the environment or the object?
Object. So the input is the image, and the object is the glass,
Okay.
right? And the input. Well, actually, I see a point now. Input is defined as the
entire image,
but it is like the we expect it to be inputting the image of a cow, Right? We don't look at it as cow, grassland. We just look at it as cow image
Okay.
and cow label output. So that's kind of what it means by invariant relationships. Where the input refers to the input object itself and not the input with the environment. And a model that bases its predictions on an invariant relationship is an invariant predictor, and that invariant predictor is basically what we want to obtain, right? That's our end goal. So that's the general task description. There are a couple of methods that are used for risk-aware optimization. The first one is empirical risk minimization, which is basically correcting the worst group performance by importance reweighting. That's basically saying that we have groups 1 through group 4, and we say that we weight the error between the groups equally. So we don't care about the average error anymore. We weight it by the proportion of the data that is present, and that way we can basically get a loss function that will minimize to the average error of these or the average error of these domains rather than the average error of the labels itself. So instead of traditional likelihood maximization, it minimizes the average loss across domains rather than across every single data sample. G basically refers to the groups, so groups 1 through 4. And I mentioned that that we don't generally have this group information, right, in our training data set. We only know we have this is an image of a cow and this is an image of a camel. We don't know what the background is. So a very interesting method of empirical risk minimization is just train twice, which basically the entire process of this is the high level for a whole as paper in this one paragraph, but the idea is that you train on your spurious correlation. So the cow in a grassland and camel in a desert, and there is one assumption that they make, and that is that you need to have some images of cows in deserts and camels in grasslands, otherwise it would not work. But the idea is that it runs the entire training sequence and gets the predictor, right? And this predictor is very prone to spurious correlation. You train your entire, you evaluate the model on the entire data set, and you will get, say, 99% accuracy. But the thing that they do is they focus on the 1% accuracy. They reweight those 1% that gives an error to a very high degree, and then retrain it again. And when they retrain it, since those weights got a higher, or those cases when in the cow is in the grassland when the cow was in the desert and the camel was in the grassland got weighted to a higher degree, it basically made sure that was no longer a minima, or like understanding the spurious correlation was no longer a minima, and it was forced to actually learn the object itself. So that is the way that they approached it, and it's very, very straightforward, but also performs really well. So the approaches that we will discuss, such as IRM and DRO, which is coming, are way more complicated, but somehow perform in a very similar fashion to ERM. But that was ERM. Does that make sense? Right? Sweet.
It's like forcing the model to not accept grass as noise, right? Or like it's forcing the model to realize that the environment has to be like that noise.
Yeah. Yeah.
The right way to do it, because you force the weighting to say like if you carry this, like you count this as a factor, then the punishment is that you'll have a lot lower loss, right?
Yeah. And even the interesting thing is that after we apply ERM, the obvious, I mean this is obvious, but the traditional loss that we get is going to be much higher than that of what we get in the case of just normal training, like regular training, but it's still technically we know that it is better. So that is a very strong indication that the loss functions that we use today are not necessarily an indication of how well the model is performing. So just saying I have a model that gives us 99% accuracy or no loss, it is not a good enough predictor. It's just simply if anything, an indication that you are over parameterizing your model, which is kind of funny. But getting back to invariant risk minimization, a more robust method, I missed the word, is to define group invariants by default. So we mentioned that we have two groups, right, grassland and desert. We basically define within invariant risk minimization, they basically take a causal approach to the same problem, right? They define a structural causal model for the data generation process, and this varies by data set. And they perform a causal correction on the data, and once they basically perform that causal correction, that allows them to sort of discover the fundamental fundamental difference between the two objects. And I will make that clear in a second. But before that, let's cover more of the high level. Okay, they generate a high bi-level optimization task where there are two objectives. The first one is minimizing risk that they will define in the thing that's hidden, and actually make relevant predictions, because if it cannot make relevant predictions, it's effectively useless. So they phrase this as a penalized loss, where we have lambda, a hyperparameter that balances the prediction power and the amount of invariance that we define. So we basically expect invariance between the representations of camel in desert and camel in grassland. So we force that sort of invariance. That is what the causal correction is. And forcing that causal correction, we do it to a certain degree, almost like a sort of regularization term. So that because if we are too strict with the with the invariance, then we will basically force all of the images to look exactly the same, even though they may not be exactly the same. So it restricts the expressivity of the model. So if everything is invariant, right, what will end up happening is we will expect the direct representation of cows to be 1 and camel to be 0, not throughout the entire extent of the model, through the single individual layer that we define invariance, which is impossible for us today, because whatever that fundamental property was, we need an infinite amount of width for it to be the universal approximator. So we are basically enforcing that. That's not an option for us. D represents the loss specific risk. So it evaluates a loss based on, or it evaluates a loss that is corrected for the environment. But the important crucial thing to note is that it requires the fact that we need environment information. So without information about the group, it is not possible for them to create or establish that invariance. And R and E over here is basically the predictions against the data, and then it evaluates the risks through a formula that is so ungodly I cannot understand it. But if you guys want, I can pull it up. I think I have it.
Can you go over the last one more time? I'm a little confused.
1 second. I have it like right here. One of these tabs.
Shannon Jensen, lost is what it's familiar right now.
What? Sorry?
The Shannon Jensen was
Oh. This is IRM.
How do we exactly define what risk is specific to a group? Like, is there a formula to, like, based on the environment for evaluating the risk?
1 second. So it's this is the definition for the formalized definition for the risk. We basically evaluate information against the. Wait, let me zoom in.
Based on the loss of.
Okay, let's break this down. Environment given.
Is that the expected loss?
Yeah.
Yeah, so risk by itself is just a numeric value, like similar to loss, but since it's not actually technically loss, we don't call it loss.
It's like group specific loss?
Group specific loss.
Okay, I see.
Yeah. It is the risk under environment. E contains all of the possible. This is the spread of modern realism and possible worlds.
I think it's the expected loss for that one, because, like, if the loss we pass in x and y, where x is like
Mhm.
our image and y is that for an e is like for that
Environment.
particular environment.
Yeah. Yeah.
And like okay, I see.
That makes sense.
That makes sense.
Risk counter environment E is basically loss specific risk or loss environment specific loss, but the actual function that they are using that I think they said is the practical is this, where they this is looks ridiculous, but the idea is to realize that the right bit is just a regularization term with the lambda attached to it, and that is again the hyperparameter. So that is the one that is defined 0 through infinity, balancing between predictive power. It is an ERM term, and then the impedance of the predictor itself. But if that does not make complete sense, I'm with you guys. Anyways, the distributionally robust optimization or DRO is also another interesting approach that this extrapolation actually uses. So it's very interesting. Risk extrapolation it almost combines these three approaches that we discussed earlier, and we will see in the formulas that they define that it's setting certain parameters a certain way will basically recover either one of IRM, ERM or DRO based on whatever approach we're using. But when we have only a single domain or a group, it is common to assume that the probability of y given x is fixed. That is, if we have 50%, if we have only one group, so we have cows and camels, both of them are in grasslands, we have 60% camels and 40% cows. The assumption that the model makes is that you will 60% of the test data that it gets is a camel and the 40% is a cow. So that is sort of information that it assumes about the distribution itself. It's called the covariate shift assumption, and this approach it does not make that assumption in order to evaluate the approach. So it is very, very robust to covariate shift, which is one of the biggest contributions that the paper makes, because besides that it is pretty similar to IRM and ERM. But for data containing multiple domains, test distributions are assumed to be convex combinations of the training distribution. What I mean by that is basically every single domain is considered an affine set, and we basically pull out a permutation of the said affine set. And what I mean by that is we define a linear combination, right? But all of the priors that we define, so what we multiply against, sum up to 1. So that's just an affine combination. So we want to maximize with this DRO, and I specified RI over here, which is risk interpolation, but that's the same as DRO. It's just two ways, they're synonymous. So the objective is to maximize the number of environments when the number of environments that it is robust to, given the lambda sums to 1, and every single individual lambda is either 0 or greater than 0, and we basically said, what is M again? M should be, M is the number of environments. We compute the weighted risk for each of these environments. So it's almost a form of reweighting where we assume we have a combination of our test set is a combination of the past domains, right? So quite similar to ERM when we reweighting it. This is sort of a more intelligent method of doing that same thing, because we sort of make some priors about, or assume some priors about the test distribution and train according to that test distribution. So the idea is that the risk effectively is displayed or graphed as a convex hull of these training distributions. So we have E3, E1 and E2, which are 3 independent training distributions, and what this method allows us to do is basically interpolate between the 3 distributions. So if we have a certain set of E1, E2, E3, regardless of the proportions, it will fall within this bracket, right? And the risk interpolation basically corrects for that. And the proposed approach, that is min-max risk extrapolation, basically allows us to extend our risk outside these sort of boundaries. So instead of just interpolating within the distributions, even if we see a somewhat unseen distribution, it should be able to make a relevant prediction. So that is our end objective would be to have the perfect prediction or a very relevant prediction regardless of the regardless of our test distribution. It could be completely unseen, but that is something that is simply not defined in this work and is the impossible problem basically. So that's risk-aware optimization, or the three techniques for risk-aware optimization that we covered. Now looking at risk extrapolation, right? This is the actual algorithm that was proposed in this paper. Minimax REX, it fundamentally extrapolates on DRO, so it is just an extension of DRO, right? So over here, the only main change, not only main change, the only change that it makes is it defines a hyperparameter called lambda min, and that lambda minimum is like the minimum value that it proposes. So it's almost a sort of directed reweighting. Lambda minimum is a hyperparameter. M is the number of domains. This was supposed to be on the previous slide. But anyways, the formula you can see is exactly the same, except instead of greater than or equal to 0, we specify greater than or equal to lambda minimum. And that basically expands into this function that is more computationally tractable. But the idea is that it extrapolates on the convex combinations. The idea is that by setting lambda minimum, we are able to extrapolate on the actual region itself. That is because when we set lambda minimum as less than 0, no, that is not because of that. Sorry.
I thought it was because you're defining a lambda minimum because you don't want to go all the way back to 0.
Well, so you could set it to 0, and if you set it to 0, that would give us DRO. DRO works very well too.
I think the extension that they're trying to make is I think DRO basically is weighted proportionally.
Mm-hmm.
But this one gives more importance to the weights that are the worst performing because we're setting a lambda minimum. Because lambda minimum, I think that what it does, because it's greater than that, it's not gonna give any parameters to those who are already performing very well.
So, well, let's see what happens, right? Suppose we set lambda minimum as 0.01, right? That would basically mean that it would not negate any of the domains, right? Because if lambda E for any environment is 0, then it will basically ignore the risk for that domain. So it's by setting lambda minimum, it defines or it forces there to be at least some degree of contribution, but not complete degree of contribution.
Right.
It
It's
cannot
more
be
control. You have more control over the DRO model.
right. But I don't see how that extrapolates though.
But I think isn't the point that if you see the second one, I think it says when it tends to negative infinity, it enforces equality between training tasks, right? So
Right.
essentially, if you don't stop it anywhere, it makes sure that the loss in each of the groups is the same. There's no difference.
Yeah. So not the loss, but the risk.
The risk, yeah.
So it's that. I guess that could be it. That makes sense.
So as a question, what will happen if you set it equal to 0?
If you set it equal to 0, it's just
Basically,
this.
DRO.
Oh, okay, so you go back to that. Okay.
Yeah. But if we set it to say negative infinity, it will extrapolate infinitely.
Yeah, so we'll extrapolate.
And that's the thing that you were saying, that you need an infinite width,
Right.
so that to like get that fairness, like the proposed definition of fairness, you need
Uh-huh.
it for it to go like infinite width.
Right. So the that makes sense. That makes sense. Okay. Awesome. So right, if the minimum lambda minimum is less than 0, it sets negative weights to all except for the worst performing group. That's programmatic. It's not represented mathematically, but that's basically what it is doing. And as lambda minimum tends towards infinity, it basically requires all of the risks to be equal. So if the error rate for group 1 is 20%, that should be the same for group 2, 3, and 4, and that would be defined as a fair model, not a perfect model, but a fair model. So this is not really machine learning, but some people are trying to enforce this fairness, this definition of fairness, and say that you want to minimize for fairness and not general loss. But it doesn't make complete sense in a practical setting unless we are able to make sure that the risk overall is extremely low, which is also rare with our current understanding. So that is minimax risk extrapolation, and that's what basically is defined in the paper itself, and that is like the theoretical ideal. But when actually run in a practical scenario, they found this sort of gradient map, the one on the left, that is extreme, that is super extreme, and because of that it is very, very unstable. So the loss that you were getting was not necessarily, it did not necessarily adhere to the it necessarily did not adhere to the global minima, or did not approach the local minima, whichever one it is able to obtain, simply because of the fact that the gradient is extremely sharp. And the way they corrected that was that made it difficult to converge. Instead, they simply used the variances of the risks in order to obtain smoother gradients for stabler optimization. And the updated function, right, it basically adds another hyperparameter that motivates risk equality similar to lambda. It's really the same, but just defined differently for some reason. We, instead of taking the summation of the risk and multiplying that by a lambda, and where that lambda is defined as your affine set of weights, so the weighted reweighting the importance. We have a single value which is evaluated or multiplied by the variances of all of the risks, and as the beta tends to infinity, we are motivating risk equality, and that is added to the traditional definition of risk. That is of the sum risk across all of them, where lambda is, if it existed, it would be just equal to 1 for everything. And yeah, that's the variance based risk extrapolation, and it performed very, very well, and which we will basically see now. So their approach performs pretty similar to ERM and IRM for these data sets or these benchmarks, right? They are domain generalized benchmarks, so their entire objective is to have a different test distribution from a training distribution. Normal models perform awfully on them, but these are basically all of your top performing examples. We see that they perform, that VRX is not like incredibly better, it is somewhat better by a minor amount, which somewhat makes sense because the entire idea of this paper was risk extrapolation, and this benchmark technically tests interpolation. So it performs similar, which makes sense. It is a little bit more generalized, which also makes sense. But when we induce a covariate shift, so the distribution changes regardless of the environment itself, right? We see that VREX or variational risk extrapolation outperforms IRM on dataset variants that include domain shift. So yeah.
Can you give me an example of a covariate shift?
Oh, there is no real example of a covariate shift. Like,
wouldn't that just mean like you take the cow and put it in an environment which is not in the Eventual domain?
No. That is domain shift.
Yeah.
Okay.
That's domain shift. Covariant shift is where I have all of my images in one domain, okay? And 50% of my test training images are camels and 50% of my training images are cows, okay? And we generate a predictor. And the predictor, it also understands the fact that the chances of it being a cow and camel at priors is 50%, so it is balanced, right? But if 90% of your test images are that of a cow and 10% are that of a camel, that becomes your covariant shift. And it will result in the model learning that distribution and trying to enforce that distribution. So that is a problem, and we do not want that, because then again it is learning implicit information that is a correlation but not a causation, right? You would not expect all of the information to have the same distribution, but for some reason, well, not for some reason, but for whatever reason it does in any normal setting. So in this case, we can see that with VREX, with the extrapolation, it is actually a lot more resilient to do the covariant shift, and I think this is in terms of reducing covariant shift.
That would make sense because you're accounting for the variance in the gradient. Because you're smoothing it out. So like it doesn't matter if it's like 80 or 20, at the end it's gonna look somewhat about the same.
Right.
Can you explain it?
Isn't it like, I think the point was that if you have like let's say, let's just define like 50-50 is like a smooth distribution.
Sure.
And then 80-20 would be like kind of like it would look weird when you like the gradient. But if you account for that variance, right, and you smoothen it out based on the variance, then it would kind of look about the same. Like in the sense that it would be just shifted, but it wouldn't be like very edgy and sharp.
It won't.
Yeah, like, so if we go back to the previous, right?
Yeah.
Like the previous slide.
Oh, well, no, I don't think that's.
Isn't that what it's like? So you look right here, right? So that the VREX basically accounts for the variances.
I think the variances are just as a method of smoothing the gradients rather than changing the gradients itself.
No, it's
So-
yeah. That's my. But isn't that
Okay.
why it's better?
That is why it is better. Yes.
Yeah,
that is why it is better. But I don't think that is to do with covariant shift. Could be wrong, right? I'm not 100% sure on this information myself. But the my understanding was.
Oh wait, no. Okay, I see. The variance just like it makes sure that like the optimization is stable.
Yeah.
Okay.
Like it makes sure that the optimization is stable and it's working on the risk itself, which is different from the covariant shift.
Okay.
So
Then how does it account for the covariant shift if like it's not? Or is that encoded in like the risk? Because the risk would basically
Yeah.
be a proportion, like the group would be proportion.
I think the that is encoded within the disk itself. Let me see if I can.
Because this question was right, like the covariant shift, like it's didn't see anywhere in the formula where it's accounting for it. It does account for domain shift because
That's the-
that was the risk, like the different groups.
Right.
But I don't. Every formula that said domain shift, domain shift, domain shift.
DRO is by default robust to covariant shift.
Yeah, I think you
So-
explained that you were like it doesn't care like how many.
Well, no, covariant shift.
Like in the DRO, I think you said something like at the start that the implicit encoding like there's 50-50. DRO doesn't care about that. Like starts, it looks at like one thing from the start. If you like go back to you say when a single domain is available, it's common to assume that the probability of
It's
ionized space.
interpolated, I agree, right? 'Cause
Well-
it's somewhere like in our actual interpolation.
Yeah, so it says REX does not make that assumption. So essentially, it's like resistant to covariant shift.
Well, right, but what does it mean to establish a covariation assumption in terms of the formalization? Because it is minimizing just the risk interpolation, right? That's what it's minimizing. That so I don't under.
I think it's not included here. I think it's just like you're assuming that, so you don't have to worry about it.
Okay. That I will clarify this. For you guys. That
Because
is.
it's not here, so I'm assuming because they
Yeah.
assume that they're not caring about it.
Right, but that's sort of a sad explanation. Why is
I
it?
know that's
Just
what
because.
yeah, I know.
But yes, okay, that is something that I need to clarify. But yeah, I think that's everything that I had. It performs a lot better on covariate shift. I don't know how well this performs against DRO, which is something that is interesting because they do not report that within this within the results. Like that is the complete result table that I got. But
They don't publish, that's why. They don't publish, that's why.
okay, but yeah, that's
For the first one, it was like it's about the same as like 50-50 chance.
right.
I think it did well.
Okay, but yes, that is all I have. Thank you all very much for coming. But yeah, if you guys have any